All right, we are in section 7.5, looking at strategy for integration. So this really is just kind of a reflective section, so we're not learning anything new here. This is just a good opportunity to kind of review what we've looked at, try some examples of it as well, before we move into some different stuff throughout the rest of the chapter. So the idea behind this section is the idea that when you're getting an integral to solve, you're not going to be given information like use this particular method to solve this integral, because that's not how it works. So when we see an integral, our goal is just to solve it using whatever means necessary, and we're not indicating which method to use necessarily. So we need to be able to identify the method of integration that we need to use. When we cannot immediately integrate, we can follow this process. So generally speaking, simplify the integrand if possible. Look for an obvious substitution, because if you can find like a u-sub for it, then that's always going to be preferable to doing some of these other methods. Classify the integrand according to its form. So does it have the form of a rational function where we might use partial fractions? Does it have the form of an appropriate radical function where we might use trig substitutions? It just depends. So classify it, and then if all else fails, then try again. So you might think, oh, this one looks like I'm going to use, trig substitution for it, and you start going through it, and it's really not working. It's not getting you anywhere. Maybe go back and try again. Maybe there was a u-sub that you missed, or maybe you could have done integration by parts on it, and maybe you didn't realize that. Or maybe, this is a complicated rational function, and partial fractions is going to take so long, and then you look and you could have simplified it, or something like that. So there is no one way to be able to say, oh, this is definitely this type of integral, but through practice and through looking at lots of examples, you can get a pretty good idea of recognizing these patterns in the integration. So, and then also remember, there are basically only two methods of integration, that is substitution and parts. Pretty much every technique of integration we have boils down to one of these two in some form. So just bear that in mind when you're looking for methods to solve these different integrals. Okay, if I can get this up, there we go. So we're just going to look at a bunch of examples here. For this first one, this one's pretty interesting because there are actually two different ways to get to this answer. So I'm actually going to show you guys two different solutions to this, and we'll see that both come to the same place. But I think it's great practice to see that there sometimes are more than one way to do these. So, but this one, hopefully you can recognize pretty quickly that this is going to require, this is a trig integral, right? Trigonometric integral. So we need to play around with some identities and whatnot until we're able to get it to a form that we can solve. So I'm going to set this up. So I'm going to do solution 1 and solution 2. So solution 1, I'm going to take the 1 over cosine cubed and turn it into secant cubed. So this becomes tangent cubed x times secant cubed x dx. Okay. And then now we can start playing around with how we might need a trig identity. So I'm going to pull out one of the tangents and one of the secants. So that leaves me with tangent squared x times secant squared x times secant x tangent x dx. Because now I can turn that tangent squared into secant squared minus 1 using a trig identity, and secant is going to be my primary function, and that is its derivative. So that's going to allow me to use a u substitution. Okay, so these are the kinds of things that you'll start picking up when you look through more of these problems and find the patterns with all of these. So we've got integral secant squared x minus 1 times the secant squared we already had, times secant x tangent x dx. Okay. And now we can let u equal secant x, so then du is secant tangent, so secant x tangent x dx. So this gives us integral of u squared minus 1 times u squared du. So we get u to the 4th minus u squared du. So that's u to the 5th over 5 minus u cubed over 3 plus c. And then sub back in our u value, which was secant. So this is going to be 1/5 secant to the 5th of x minus 1/3 secant to the 3rd of x plus c. And that would be one way we could solve this problem. And now I'm going to go in and do solution 2. So maybe you looked at this problem and you didn't see that relationship of 1 over cosine being secant. Maybe instead of that, you said, well, I have a cosine and tangent is written in terms of sine and cosine, so maybe I can just do this with those functions instead. So we turn our tangent cubed over cosine cubed into sine cubed over cosine cubed over cosine cubed dx, right? Tangent cubed over cosine cubed. So that's going to be the same thing as 1 over cosine cubed. So that's going to be sine cubed over cosine to the 6th dx. And we're always looking for that odd power, and notice we have an odd power of sine. So that's going to let us, I'm going to keep this as sine squared over cosine to the 6th times sine x dx. Because now I'm going to use my trig identity, turn sine squared into 1 minus cosine squared. So we have 1 minus cosine squared x over cosine to the 6th of x times sine of x dx. Here we get our u sub, so that u be cosine of x. Then du is negative sine of x dx. So we get 1 minus u squared over u to the 6th times negative 1 du, because it was negative sine. Okay, so split that up over the common denominator. So I'm going to pull the negative out. This becomes 1 over u to the 6th minus, that would be u squared over u to the 6th, but cancel the 2. Okay, 2 factors, so we're left with 1 over u to the 4th du. And now let's integrate. So we have negative of negative 1 over 5u to the 5th plus 1 over 3u cubed. These are undoing the power rule, right? That's how we do these integrals here. And then plus c. Okay, and now sub back in. So distribute the negative, so that one becomes positive, that one becomes negative, and the constant, it doesn't matter because it's arbitrary, so it's not going to matter whether it's a plus or a minus, so we'll just leave it. So this is 1 over 5 u to the 5th, so that's cosine to the 5th, cosine to the 5th of x, minus 1 over 3 cosine cubed of x plus c. And now we have the 1 over cosines, which can turn into secants. So this becomes 1/5 secant to the 5th of x minus 1/3 secant cubed of x plus c. And then compare the answer we got with solution 1 to the answer we got with solution 2, and of course they are identical because they were both done mathematically correct, and we used the right trig substitutions, right trig functions, trig identities, and it got us down to a very, very nice answer in both cases. Okay, so this is just again to show you that there is more than one way sometimes to do these, particularly when it comes to using like trig identities and things like that. So a very interesting problem here. Okay, so let's look at the next one. Okay, so the first thing that we should look for is any possible simplification. So let me just put that here. So x to the 5th plus 1, that's not going to simplify the denominator. You've got a factor of x you can pull out, but nothing's going to cancel with the numerator. So there really isn't any simplification we can do here. So no simplification. Could we do like a substitution, like a u sub? Not really, because you'd have to do like a power of x, but then you can't cover all the other powers of x. The u sub is just going to be too complicated to do this one. Okay, and also not a trig substitution, because trig substitution would need to have a root of some sort, and this one does not. Okay, so that leaves us with, hopefully you recognize this as a rational function. This looks just like one we would use partial fractions for. Okay, so I'm going to just put a little check there. So this one does fit the profile of an example with partial fractions. So the only thing first we need to do is we need to take into account the degree. So we do need to do some long division here. Okay, so this would be x cubed minus 3x squared minus 10x into x to the 5th. And I'm going to have a lot of placeholders here. 0x to the 4th, 0x cubed, 0x squared, 0x plus 1. We'll go all the way down there. Okay, do the long division, so that's x squared, that's x to the 5th, minus 3x to the 4th, minus 10x cubed. Subtract all of that. We're left with 3x to the 4th plus 10x cubed. Okay, so we get x cubed into 3x to the 4th, that's going to be plus 3x. So we get 3x to the 4th. I can bring down these other placeholders, or at least one of them. And then that gives us minus 9x cubed, and then minus 30x squared. Okay, so that gives us 19x cubed plus 30x squared. And you can see I'm starting to run out of room here already. But x cubed into 19x cubed, so that's just going to be plus 19. So this is going to bring us down towards the end of the long division. So that's 19x cubed. 3 and 19 that's negative 57x. And then 19 and the negative 10, that's negative, that's negative 190x. Subtract. It's going to give us 87x squared plus 190x, and then plus that 1 that we still had left over there. So the partial fraction decomposition, or excuse me, we're not even to the partial fraction decomposition yet. We get x squared plus 3x plus 19, so that's going to be the nice part to integrate, plus the remainder is 87x squared plus 190x plus 1 all over that common denominator. So we have x cubed minus 3x squared minus 10x. And then dx. Okay, this denominator actually does factor quite nicely, so if you pull out the x, you're left with x squared minus 3x minus 10, which becomes x minus 5x plus 2. Okay, so the next thing to do would be to recognize which cases we're utilizing here. So I have distinct linear factor, distinct linear factor, distinct linear factor. So these all fall under case 1 of the partial fractions. So we would need to set up a7x squared plus 190x plus 1 over x times x minus 5 times x plus 2 equals a over x plus b over x minus 5 plus c over x plus 2. Okay, and then we would solve for a, b, and c. I'm just going to tell you what they are because this gets these numbers in this particular problem get quite ugly. So dot dot dot. If we go through the work, we get a is negative 1/10. B is 3,126 over 35. And C is negative 31 over 14. So as you can see, not a very clean answer we're going to get here, but once you get those, you do the partial fraction decomposition, okay, and then you can integrate it. So let me give you the final solution here, final answer. So you're going to get 1/3 x cubed plus 3/2 x squared plus 19x minus 1/10 ln of absolute value of x plus 3126 over 35 ln of absolute value of x minus 5 minus 31 over 14 ln of absolute value of x plus 2 plus c. So we get a pretty ugly final solution on this one, but that would be how we get there, just using the same methods that we were using before. So you do the long division if necessary, and then factor the denominator, set up your decomposition, okay, equate your coefficients, right? So multiply your LCD, equate your coefficients, solve for a, b, and c, plug them back in to the integral, and then take an antiderivative. And you're going to get just a whole bunch of string of terms here, but it's the same process that we used in the previous section. Okay. So let's look at the next one. So we have integral of dx over x times the square root of ln of x. So in this case, again, we start running through our checklists here. This one doesn't simplify at all. Can we do a substitution on it? Well, in this case, because I'm noticing this doesn't really look like the forms that we have been talking about. However, if you just see what happens, let's let u be the natural log of x. See if we can simplify this without going to too much trouble. Then du would be 1 over x dx. And notice what we have here. This gets covered by u, and 1 over x dx gets covered by du. So this actually simplifies to 1 over root u du. And this is actually an integral that we can take using our Calc 1 methods. This is the integral of u to the negative 1/2 du. Undo the power rule, we get 2 root u plus c. So that just becomes 2 times the square root of ln of x plus c. So this is a far cry from the previous example, but that's the thing, is that sometimes your integration can be done a lot more simply than you might even realize, which is why it's always good to look for substitutions first, because you could stare at this for hours and hours trying to come up with one of the more complicated techniques, when it turns out it was going to take you 2 steps in a u-sub. So just always be on the lookout for the different types of integrals that we have encountered, because you never know when you might need them. Okay, and then let's look at this example down here. We have integral of e to the square root of x dx. So let's try our strategy again, where we utilize a u substitution. See if we can do something about this. So we're going to let u equal the square root of x. Then du is 1 over 2 root x dx. So this doesn't seem to indicate that it's going to be too helpful because we don't have one of those in the function, but if we get a little creative with it, so since u is the square root of x, can everybody agree that x squared, or excuse me, u squared is equal to just x? Right? If we square both sides of this, we get this. So u squared is equal to x. And in that case, dx is 2 root x times du. Alright, think about that relationship. Multiply 2 root x to the other side, and you're left with this. And then root x is just u. So that's just 2 u du. So we can actually, through a little creative math work here, we can use this and this to make a substitution. So this is going to be, let me use a different color. This is going to be the integral of e to the u times 2u du. So pull the 2 out, integral of u e to the u du, and then this is something that we can integrate using integration by parts. Okay, so in this case we're using a conjunction of a u substitution with a little bit of creativity thrown in, and integration by parts. Okay, and the reason we had to get so creative is because integration by parts, we actually had to make this more complicated in order for us to be able to solve it. So, but a very interesting setup for this. So for integration by parts, okay, I'm going to use v and w instead of u and v because I don't want to get it mixed up with this u. So v is going to be u, dw is going to be e to the u du. So then dv is just du, and w is just e to the u. Okay, so if you need a little refresher, go back and check out that integration by parts work we did again. So this is 2 times, we have u e to the u minus the integral of e to the u du. Okay, and that's integrable. So we have 2u e to the u minus 2e to the u plus c. And then sub back our u value, which is the square root of x. So we get 2 root x times e to the root x minus 2e to the root x plus c. All right, so this is just a little bit of work with different types of integrals, different things you might see or encounter. Obviously, some of these are differing levels of difficulty, but so are all problems, right, in math. This brings us to the end of section 7.5, just kind of summarizing everything we've talked about so far, because when we come back in the next section and the rest of chapter 7, we're going to be looking at still integration, but it's going to be a little bit different than just these straight up techniques that we've talked about so far. So that brings us to the end of section 7.5, and I will talk with you all next time.